All right, folks, so we are here at the very last section of chapter 3. And so throughout, we've been using these fixed basis functions, and I guess he's just going to chat right now a little bit about why this is going to be restricting and point towards future chapters where we talk about how to get around this by using adaptive basis functions, basically. So we have focused on models comprising a linear combination of fixed nonlinear basis functions. The assumption of linearity in the parameters led to a range of useful properties, including closed form solutions, which you almost never get, the least squares problem, as well as tractable Bayesian treatment. And for a suitable choice of basis functions, we can model arbitrary nonlinearities in the mapping from input variables to target. So, if your data is, like polynomial, just put in some polynomial features and you still get all the benefits of linearity, but with allowing, the use of nonlinearity as well. Next chapter, we shall study an analogous class of models for classification. Okay, cool. So it might appear that such linear models constitute a general purpose framework for solving problems in pattern recognition. Unfortunately, there are some significant shortcomings with linear models, which will cause us to turn in later chapters to more complex models such as support vector machines and neural networks. So that's going to be, I think, chapters 5, 6, and 7. Okay, so the difficulty stems from the assumption the basis functions are fixed. So exactly, before the training data set is observed, and the manifestation of the curse of dimensionality. So basis functions are fixed. And the consequence, the number of basis functions needs to grow rapidly because you don't know where your data is going to lie in your space, right? So and as your space is growing exponentially, so you're going to need to have exponentially more of these of your basis functions to kind of capture all the different directions data could live in. So this is the problem, right? This is when if you don't adapt your basis functions, then in the large high dimensional setting, you're going to need way too many of them, basically. Okay, fortunately, there are two properties of real data sets that we can exploit to help alleviate this problem. First of all, the data vectors typically lie close to a nonlinear manifold whose intrinsic dimensionality is smaller than that of the input space, or the extrinsic dimensionality, as a result of strong correlation between input variables. So this is the key thing, right? If the data really was high dimensional, then you'd be hooped, right? So the point is that most, well, let's say data sets that we can actually kind of learn from are the ones which, the variables might show up having lots of dimensions, but actually they lie on a low dimensional, on a low dimensional data set. So those elements are going to be correlated with each other in such a way that if you plotted it out, you would see that, look, it's this two-dimensional manifold in a 100-dimensional space. Okay, so we'll see an example of this, and I think I should actually highlight like close to a node is smaller than the input space. Okay, so if we're using localized basis functions, we can arrange their scattered input space only in the regions containing the data. Yeah. This approach is used in radial basis function networks and also in support vector and relevant vector machines, which you'll see. Neural network models, which use adaptive basis functions having sigmoidal nonlinearities, can adapt the parameters so that the regions of input space over which the basis functions vary corresponds to the data manifold. Right. The second property is that the target variables may have significant dependence on only a small number of possible directions within the data manifold by choosing direction of input space to which the basis function responds. That's kind of interesting. So yeah, so I guess he's also saying that another way you could, suppose it's possible that your data was high dimensional, but only a small number of dimensions actually determine the targets. Well, then you only need to kind of focus on those, at least in kind of classification settings. So that's kind of an interesting point. So I'm going to highlight that as well. But I guess we're going to see all of this in the coming chapters. So we'll kind of talk about it then. Only a small number of possible directions. Great. Okay, so I think that's basically kind of the very small coda to this chapter, kind of setting up what's coming up next. In the next video, I'll just do an overview of what we've covered. I think we've covered a lot of really important material in this chapter, so it'll be useful to kind of go through it together at that point. But yeah, good. So yeah, hopefully you've learned some stuff so far. As always, just let me know in the comments. We'd be happy to hear from you, and hope to see you in the next video.